Here, I don't know where we stopped, but I have to maybe repeat that the starting point for the paper in Nature 8 years ago. The paper was about the top 100 papers, the most cited research of all time. Then if you look on the list, you see that basically there are 5 papers, if I remember, devoted, which were related or awarded later by a Nobel Prize. And the most fundamental development, like double helix, high TC superconductors, or black energy in astrophysics, is not included in the list because it's not important enough. Also, Maxwell and Einstein is absent. Here if your paper is so important, like special relativity, you immediately go rather to textbooks than to newspapers. So, and in general, if quotations are organized as Mount Kilimanjaro, you will see that 1 centimeter of its height is those most quoted papers, and about 1/2 of papers is not quoted at all or quoted 1 time. So you see that we have this pyramidal organization of papers. The most important techniques, or other fields, if you look on them, because we are speaking about all scientific papers, not only physics, it's related to biotechniques, biology, bioinformatics. When we have papers about experimental techniques, how to get out protein from a solution, what the genes or proteins do, and so on. Now also phylogenetics. So this is what we have: different species, and we have some relations between them, and we also have evolution of those relations. So this is quite an important piece of science today. Statistics. Statistics not in the mathematical size, but again as applications. We have a tremendous number of data acquired by computers right now in laboratories, and we have to make something reasonable out of it. So organize it, check what is the confidence of the final results, compare various, for instance, various species and genes in various species and so on. Now, DFT comes here at the 5th place. There are 2 papers in top 10 papers and 12 in top 100. This is, again, not a basic situation like Dirac equation, but the DFT was a method to compute physical properties of solids and of molecules. So it was important both for physics and chemistry. And the popularity grew with the package, Gaussian or other packages in condensed matter. I will speak about them later. And this is quite important. I mean, this is like quite an important piece of progress in science. It was developed, it was provided by DFT. And finally, we have crystallography, but not in the sense of crystalline structure of silicon, but rather structure of biology. Well, for instance, in the crystallography, we have a paper on the number of 23, comes from our colleagues from Warsaw University, Minor and Otwinowski. They moved to United States and then developed some very popular method of identifying the structure, biological structures. So if you look on this list, you see that Professor Sosnowski, the founder of our physics in Warsaw, physics of solid state, was quite right, because he said, don't try to be clever, be useful. So the most important scientific breakthrough papers are less important than a useful paper that provides you with a technique that you can use on your everyday laboratory activities. The density functional theory starts with the paper, but judging by the size of the letters, you can see that the important feature of this paper was that it was published in the Physical Review. And the sort of non-important detail was that the author was Schrödinger. And this is the paper in which Schrödinger proposes his equation, so wave mechanics, the foundation of wave mechanics. And he also, well, it is his equation and also solutions for hydrogen, for the hydrogen atom. So he was able to immediately show that this equation is really working and will help us understand what is going on with at the atomic level. The Schrödinger equation was solved by him in this paper for a one electron system, hydrogen atom, and it was in 26, excuse me. Now the people realized immediately that we have to generalize to include relativistic effects in this equation. And the next thing, even also important, equally important, is that we have to move to many body systems. And both issues were difficult to solve, but going to Dirac equation was much faster than going to good, accurate solutions of the many electron systems. The two most important and the simplest two electron systems are helium and hydrogen molecule. So 35 years later, after the Schrödinger paper, we have papers which are described with the satisfactory precision corresponding to our experimental resolution, in which we have a solution for helium atom and for hydrogen molecule. You have Peckeris here, and I just put one of the equations of this Peckeris paper. He uses variational approach to solve the problem, and you see that the complications coming from the fact that we deal with two electrons are quite impressive, graphically at least. And you can imagine that if you have 10 electrons, this way of solving problems would be rather non-realistic. A similar situation occurs with this famous paper by Kołos and Wolniewicz. It is 68, and they use variational approach to deal with the hydrogen 2 molecule. So it was clear that something must be done to simplify the situation. Now I will quote two papers by Dirac. The first one is 29, when he observes that the general theory of quantum mechanics is now almost complete. We understand physical laws, we understand the whole chemistry, but the difficulty is that the exact applications of this law leads to equations much too complicated to be solvable. As we see, it is already for 2 electrons is true. So we need applications, we need some approximations. 1 year later, he made a fundamental observation, because he says, we have a many electron system, and each wave functions associated with the electrons will give rise to a certain electric density. Today we say electron density. So if we add all these electric densities from all the wave functions, you obtain total electric density for the atom. And now, if we adopt equations of the self-consistent field, like in exchange, so we're speaking Hartree-Fock, the value of the total electric density at any time is given, then its value at any time later is determined by the equations of motion. This means that the whole state of the atom is completely determined by its electron density, and it is not necessary to specify all individual wave functions. So one can deal with any number of electrons by working with just one matrix density function and not complex three-dimensional wave functions. Further, Wilson said, the important question remains, does there exist some procedure for calculating the density which avoids altogether the use of 3n dimensional space. So here people in 1963, Wilson is not the only one, of course, to work in the field, understood that we can use density as the basic variable rather than wave functions. Now we move to 64 and 65. We have the Cohenberg-Schoen and Kamm equations, and this is a prescription that is later used to realize this program proposed or sketched rather by Dirac. So we use the mean field approximation. So this is we have to solve one electron equation, one particle equation, and all other electrons provide some mean field in which this electron moves, but it should be, the solution should be done in a self-consistent way as proposed by Dirac. So we have a simple form of the equation. We have a Coulomb wave function with the potential, which is, of course, something which comes from nucleus or nuclei. We have a classical Coulomb potential. Here is the density of electrons. And we have additional exchange and correlation coupling included here. Of course, the density, you run over all occupied states. You possibly include spin polarization, and you get the density. So you put the density here, you get the potential, you solve for the next with the next step wave function, and so on. This is a self-consistent circle, which you stop when you get the required accuracy. So the electron-electron interaction in this way is considered, is broken into three parts. First, we have Coulomb, classical Coulomb interaction described by the second part. Then we have the exchange term and the correlation contributions. And I will start by the Coulomb coupling, in spite of the fact that we know helium atom, how it looks like. There are some features which are nice, and I would like to stress them here. What is presented in this figure is that we have helium atom in two charged states. Helium plus with one electron and neutral helium with two electrons. Yeah? Here we have 1s energy levels with one or with two electrons, and total energy with one or with two electrons. We know that helium with one electron is thus briscate hydrogen atom, so the energy of this level is 4 Rydbergs, because it scales with a charge squared, nuclear charge squared, and the total energy is also 4 Rydbergs, just like for hydrogen. Now, if I put the second electron, the situation is such that this level is no longer at minus 54, but jumps to minus 38. And the total energy is decreased to minus 75. And this is because of the electron-electron interaction. Normally, if they don't interact, you just get the double of it, so minus 108. But Coulomb repulsion between electrons raises this energy up. And this is displayed also, or reflected, in this 1s state, moving up from minus 50 to minus 40. So the effective Coulomb interaction here is about 30 electron volts. But the interesting situation is for ionization. Yes? So we have neutral atom, neutral helium with two electrons, and we ionize it. So we excite one electron, we take it from the 1s state and put it at the infinity. So you would say that on the first side, the required energy to ionized helium atom is 0 minus 30, so it's 38, 39, almost electron volts. While if you look on the experimental ionization energy, it's not 38, but it's 23. So it's this total energy difference between ionized and neutral state. And this is due to the fact that if you excite this one of those electrons, the second one immediately realizes that it's no longer repelled by the first one. And it can go to the true 1s orbital of helium plus. So this ionization energy is reduced by the reconstruction, or how to say, the shrinking of the wave function, because the electron-electron interaction is absent in this case. So we have that ionization is just the difference of total energies, and one electron levels do not correspond to changes in total energy. Now, the same situation may be found in semiconductors. For instance, we have cobalt in zinc oxide. This is alpha, so this is the absorption. We see 1, 2, and 3 peaks. We know that the first peak does not lead to photoconductivity, so this is an internal transition. We know very well that it can, that we know Coulomb in 77 resolved this transition, and it really, this is an internal transition, not ionization. 2 electron volts, and they are two transitions which are higher in energy. And from the theoretical side, we've been working with on this problem of cobalt in zinc oxide, and the last step is here illustrating this lack of correlation between total energy and levels. This is cobalt 2+, neutral. This is a level of cobalt which lies 3.5 electron volt higher. So you may think that the ionization, this internal transition, would correspond to 3.5 electron volts, which is not the case, because after the ionization, the true experimental result is 2 electron volts, because the D shell reorganizes itself. This level goes down, lowering the energy. This levels go up. But the final result is that the difference in total energies is only 2 electron volts, and the excitation energy is not the difference of level energies, like in the case of helium. Briefly, shallow donors. We have a similar situation. We have a shallow donor. This problem was studied in 50s and 60s, and later even. This particular pictures come from the paper of Neville and Mott, and the issue was impurity band conduction. And this is from his paper, from the Mott paper. What he said, this is the conduction band, and just below we have a donor. So we have the impurity. In fact, we have the impurity band when we are dealing with a finite concentration of donors, because there's overlap of the wave functions. But we see 2 levels, 2 impurity bands. The impurity band, which is here, this is the lowest one, the 1s state contains 1 electron only. And if there's another electron, second electron can also be accommodated on the S level, but we have to pay U, this amount of energy. So these are not 2 different impurities or 2 different bands, but this is the same impurity, the same band, but 2 charge states, neutral and negative. I skip Coulomb blockade, where the problems is the same, because this is a little bit more complex. Right now, so we have the situation in which the same effect as in helium is just reduced in scale, because this U in helium was about 20 electron volts, in cobalt 1 electron volt, and here is 1 milli-electron volt rather. But the effect is the same, intra-orbital electron-electron repulsion. The second channel of interaction is the exchange coupling, and here I will discuss it taking as an example the free electron gas. So in fact, we can use the Gellium model. So you have free electrons in the homogeneous compensating positive background. So the external potential is just constant. Hamiltonian is simple, kinetic energy and the electron-electron interaction. Solution are plane waves, which contain the plane wave and the spin orbital, of course. If we assume that, and this is just a textbook, if we assume that there's no spin polarization, then all states are filled up to Fermi energy and with Fermi momentum. Fermi momentum is given by the density. We spin up and spin down densities are just the same. And the kinetic energy is twice, because we have kinetic energy per particle. This is because of spin, and this is just kinetic energy of individual electrons here. It is 3/5 of the Fermi. So this is because electrons are negative, gallium is positive. If you count the total energy, the charge doesn't contribute because they are the mutual Coulomb interactions cancel. So we have only the kinetic part, as I say, and the exchange channel. Here in the Hartree-Fock method, you just take the antisymmetric combination of the wave functions. We have Coulomb potential, we have the plane waves, which are the basis function, and we have to sum up over occupied states. And you get a simple, in this case, a simple expression for the exchange energy per particle. So the total Hartree-Fock energy per particle is kinetic term, exchange term, which is given here. What is very important, and I would like to stress it strongly, is that the exchange coupling is always attractive, because it comes from this anti-symmetrization of the wave function. Yes, you have a function 1 times function 2 minus function 2 function 1. So it must always be preceded by the minus sign. And if this is repulsive, then this term will always be attractive. So exchange always lowers the total energy of the many electron systems. Impact is really, in the case of free electron gas, is really dramatic, I would say, because no exchange. This is the energy scale, energy, this is momentum in units of Fermi momentum and Fermi energy. So at 0 temperatures, all states are filled up to the Fermi momentum, and the upper energy is the Fermi energy. Now you include the negative, attractive part, the exchange part. Again, you can do this analytically because of this simplicity of the problem, of the wave functions mainly. And you see that the total energy right now is really lowered from being positive, it really becomes negative. So we have a strong downshift of all one particle energies. Moreover, it's interesting to notice that the bandwidth here is 1 by definition, and here is almost 3. So the bandwidth is larger, which means that the effective mass here is smaller, is reduced from the free electron value. So the exchange part changes even the effective mass here in this situation. Moreover, we can include spin polarization. So in the paramagnetic situation, the density of spin up and spin out just the same. In the ferromagnetic limit situation, we say that all electrons are spin up and there's no spin down. Here we have some Fermi momentum taken from the density, and we compare total energy of paramagnetic with total energy of ferromagnetic situation when there's no spin down. And this energy difference is easily calculated, and you can find that it's given by the Fermi square, positive term, minus exchange, so minus this term. This is quadratic, and this is linear Fermi momentum. So if the concentration is very high, and this is very high, then kinetic energy always prevails. But if you are at sufficiently low concentrations, like in the free electron case, it's below 10 to 22, you get spin polarization as the ground state of your system. However, you think that you've got something more accurate because you improved your theory by including fundamental Hartree-Fock exchange interaction. But if you compare it with experiment, you get a disaster. For instance, specific heat. Experimentally, it's that linear in temperature. The free electron gas, it means without exchange. It's just like that, but very close values of this constant. Beryllium gives you a different temperature dependent. Pauli's susceptibility. Well, here you get a really strong error because the difference between the experimental 2 and theoretical 12 is 6 times, yes? While the free electron, no, the simplest model is almost, okay, acceptable. Similarly, almost acceptable for sodium, but Hartree-Fock just makes something not acceptable. So we see that Hartree-Fock is much worse than the free electron gas, so with the simple Hartree. The conclusion is that we have neglected something. We have neglected the third contribution, which is correlation, and they are important because they will sort of cancel the error introduced by the exchange. And here, I would like to stress this because in this approach, there's a strict definition of correlation energy. The correlation energy linked with what I will discuss in the following is just the difference between the energy of the exact ground state and the ground state Hartree-Fock ground state energy. So it will be negative. So we move to correlations. And we come back to, well, first observation is the following, that in the Hartree model, the many electron wave function was just the product. But then Fock and Slater understood that the basic thing is to make the symmetrization. And wave functions of fermions are antisymmetric. So we take the antisymmetric product of Slater determinant, in fact, to describe the wave functions. But this method applied to simplest systems, like in chemistry, simplest molecules, or even the atoms, revealed that what we additionally need here is, excuse me, no, it's okay, is that the variational freedom of this limited set of solutions, because we take only like we take here only n wave functions. So this is too limited, and then we have to include higher states, for instance, higher atomic states, taking linear combinations of Slater determinants. This is called configuration interaction. And paradoxically, the inclusion of this excited states lowers the ground state energy, because electrons in this way are more flexible to adjust to the nuclear potential and to each other. So how it works in practice, I will illustrate it with the helium atom again. So here we have the ground state Hartree-Fock variational approach, and we know that here this is a spin singlet, one spin up, one spin down, spin vanishing. We have one s orbital, so there's no orbital momentum. So in this moment, the spin part should be asymmetric and the orbital part will be symmetric. So we assume that we have some wave functions, like one s wave function, hydrogen-like, occupied by the first and by the second electron. And we proceed in the variational way. So we assume that the wave functions are, again, like this S-like orbitals with exponential decay. And we treat alpha, so the decay radius, as the variational parameter. The calculations can be done. They are not that difficult. And what you find is that the minimum energy obtained in this way is minus 7749 electron volts. And alpha is just like for hydrogen plus, but screened. The electrons see each other, which makes the wave function a little bit delocalized here. Yes. So instead of 2 electrons, the effective charge of nucleus is not 2, but because this comes from the second electron screening the interaction. Of course, this is the simplest possible wave function. You can take this one S wave function a little bit more complex, and you can obtain, instead of 0.49, you obtain 0.86 electron volts. However, this procedure, in which we have just one Slater orbital, is very simple, gives the energy which is quite higher as compared to the ground state. And I recall that we have to reduce by correlation energy, because the difference between exact and Hartree-Fock, this one, is 1.14 electron volts, and this is what we call correlation energies. And then correlations. The first thing that you can imagine is that we take, we don't say that we have the S wave function with one exponential, they are exponentials, but one decay constant. We say that we can have one electron closer to the nucleus than the other electron. Maybe in this moment, they will be more distant, and this trick will allow us to reduce the distance between, rather increase the distance between electrons, so to reduce the interaction. And in fact, it's okay, because if you assume such a wave function of this simple product, I'm here. If you assume that you have two distinct alpha and beta constant, you lower the energy and you obtain something like 2 and 1. One Bohr, this units are of course Rydbergs and or electron volts and Bohr radius. So one is just like close to what we obtain for a hydrogen atom, and it screens the nucleus, and the other is like for okay, it's strongly screened. Instead of charge 2, we get charge 1, and we get like hydrogen. So helium ion with 1 electron, and hydrogen atom, because the first electron completely screens 1 proton from the nucleus. Radial correlations is, well, as you see, just by allowing for more freedom here in the choice of the wave function, reduces energy. And the second trick that we can make is to include angular correlations, because maybe the situation is such that the electrons, if one is on one side of the nucleus and the other is on the other side, in this moment, they are more distant, and you reduce further the Coulomb repulsion. So in order to include this type of thing, you include you use not only s orbitals, but also p orbitals. So 0 and 1 angular momentum. This is s orbital. This is the famous p orbital, like 8. If you put them together, you get something which is not symmetric. And then you take the second electron and you reverse this object, and the electrons, you allow electrons to be on the opposite side of the nucleus, maybe here, and nucleus is somewhere in the middle. So you further reduce the Coulomb repulsion. So to summarize the situation, Hartree-Fock says 2 orbitals, and they are the same for 2 electrons. They are smeared 1s. Radial correlation brings 1 electron closer to the nucleus, and the second electron is like for hydrogen. And they are still spherically symmetric. Angular, we include angular here, puts 1 electron on one side of the nucleus and the other on the other side. And the correlation effects calculated in the really very, very simple-minded model, they are the following. Hartree-Fock, so the starting point is 0.49. Here you have 8.24, and to get additional half electron volt from the angular correlations. It is still higher than the exact value, but given the simplicity of this method, I guess it's quite satisfactory. And we know how to proceed further. And right now we know also what are the main ingredients of the Coulomb interaction in the many electron systems. Well, I'm sorry. Oh, now there are two examples that I would like to give here. In the 80s, the local density approach was already, approximation was already used and applied to the simplest and even the simplest systems in semiconductor physics, namely to defects and to surfaces. The silicon is one of the most simple crystals in the nature, but the reconstruction is the most complex reconstruction of the surface that we know. So here, before we go to STM, I would say that here you have STM images, and the silicon 111 surface was investigated previously by Lead or Reed. So this electron diffraction techniques, and they reveal that they are 2 by 1, very simple reconstruction. 1 by 1 means that I have the bulk periodicity reflected in space. So 2 by 1 means that I double the periodicity in one direction. 7 by 7 means that I multiply the periodicity 7 times with respect to the bulk periodicity in the 111 plane. And indeed, those diffraction experiments have shown that we have something very complex and unusual. Typical are 2 by 1, 2 by 4, 4 by 6. It's very exotic phase in gallium arsenide. And here we have 7 by 7. The geometry at the surface was rather intuitive, how to say, the matter of speculations up to 1980, when the scanning tunneling microscope was developed by at IBM Zurich by Binning and Roller, and it was immediately applied to semiconductor surfaces, and in particular to the silicon 7 by 7, so silicon 111 surface. Here you see two different images of the surface. You can tunnel the current from the surface to the tip, and you probe field states, or inversely, you can inject electrons to the semiconductor, so you probe empty space, otherwise you won't have any current. These images, as you see, are different somehow, but the main periodicity is absolutely visible here. It requires some preparations to get high quality surfaces, of course, but the geometry, underlying geometry, and plotted here was proposed by Pandey. So, and it is really amazing that such a large reconstruction required, involving 200 or 300 atoms at a time, was possible to identify and to study by those methods. And I say it was one of the really big successes of the density functional theory, to recognize where you have the side here. This is the side view. So normally the surface would end here, but you have something more. You have on this 1, 2, 3 layers more. They have sometimes atoms and sometimes not. Moreover, as you can see from here, left and right part of the 7 by 7 unit cell is not the same. It is less obvious in the empty space, in the field space image, but in the empty space image it is clear, and also the geometry. I mean, the calculations reproduce everything here. The second example comes from defects, and the nice example is the so-called EL2 defect in gallium arsenide. This defect, in the 80s, the defect was extensively studied experimentally, in particular by Professor Figielski and Jarek Dąbrowski at our institute, and Maria Kamińska, Łagowski, and many others, Baranowski, at the Warsaw Institute. And the properties turned out of this defect turns out to be complex. The issue was that gallium arsenide at the time was recognized as maybe something which would replace silicon in microelectronics, but also in optoelectronics. It was extremely important because first light-emitting diodes were heavily based on gallium arsenide or gallium aluminum arsenide conduits. And then a defect which is was just deteriorating the properties, electric and optical properties of devices. The experimental behavior turned out to be quite complex because we have the like persistent effects or bleaching. So the bleaching is the effect in which now EL2 means that we have the band gap of gallium arsenide, and there are several defect-related levels. Electric level number 2 was just the first name to this defect, which turned out to be arsenic sitting on the gallium side. So this is a piece of gallium arsenide crystal, gallium. This is gallium atom, which normally would be surrounded by 4 tetrahedrally arranged gallium atoms, arsenic atom, sorry. But if it is an arsenic atom, then we have a sort of cluster of 5 arsenic atoms altogether. Persistent effects and bleaching. If you have a defect in the middle of the band gap, you can switch on the light, and you can observe the absorption related to this defect. Yes? The experiment occurs at low temperatures. You switch on the light, and you see that the defect disappears. Well, there's no longer, after some moments, longer or shorter, it depends on the light intensity, you see no defects at all. This is called bleaching, like you are bleaching something from your shirt. And this bleaching persists for long times, but if you rise the temperature below 100 Kelvin, if I remember correctly, then the defect reappears again, and you can see the absorption line related with this defect. So it is a metastable behavior. This is called persistent effects, and so on. Dąbrowski, Scheffler, and Chaddi and Chang published the LDA calculations for the arsenic andesite in gallium arsenide in the same issue, back-to-back of Physical Regulators in 1988. And they both propose that you have a substitutional configuration, but the defect may break one of these bonds, yes, and move to the interstitial position. It is like the planar configuration of 3 gallium atoms, and it's just a little bit off plane. And this is the metastable position. By switching light, you can then, there's an energy barrier between the 2 sides. If you are at 0 Kelvin, you just stay here forever. But if you raise the temperature, the defect, the antesite, has a chance to make it through the barrier and come back to the substitutional site and to absorb light again. So that were the first computations which revealed that the structure of geometrical structure of defects in solids may be more complex than just sitting simply on the substitutional ideal lattice site. The behavior is more complex. And people immediately realized, and Chaddi realized, that we have the so-called DX centers. And they, like silicon in gallium arsenide or silicon in gallium aluminum arsenide, would do just the same. There are 2 possible locations in the lattice, stable, metastable, and there's a transition between them. And then it turns out even that the very funny effect is related with the behavior of DX centers, because DX means that we have done already something tricky. So the name DX itself comes from the period when we did not understand this bistability of the donors. And a funny factor, normally you say we have positive U because the U is the repulsion, measure of the repulsion between 2 electrons of the same center. And it is positive because Coulomb energy is positive. But experimentally, it turned out that DX centers reveal the so-called negative U effect, which is, of course, not that electrons attract each other, but they reflect the fact that we have a donor. Donor is on the substitutional site and is ionized, but then it goes here to this metastable DX position, and this shift induces the appearance of a single electron level below the bottom of the conduction band. So these two electrons can go. There's a place for two electrons. So instead of having no electron, the donor accepts two electrons, and the neutral charge state is just unstable because it's somewhere in the middle and corresponds to the energy barrier. So it's either ionized or positive or negative. I guess it's well, what I had to say. Maybe I will say that the first really the LDA becomes popular at the beginning of the 80s. And it turns out that all ground state properties, such as lattice constant, bulk modulus, even phonon spectra and so on, were correctly reproduced. But it was possible because, well, there's another technical issue, how to deal with electrons in a solid. Plane wave basis is wrong because you need infinite number of plane wave bases to describe the one state of, I don't know, like cadmium or tellurium. So either we use atomic orbitals and the linear combination of atomic orbitals, or the choice of other basis functions. That was a huge progress to deal with this problem. Or the problem was solved by the introduction of pseudopotentials, quite accurate pseudopotentials. So in the 80s was the beginning of this successful path of the DFT in the local density approximation. What accelerated very much the progress was that we have several codes. Italian Quantum Espresso, Fritz Haber Institute in Berlin with the Fritz Haber code, Siesta in Spain, Vienna in Vienna, and so on, Abinit and so on. So these codes, they are, you have a large number of those codes, they are easy to use, but people from the field often say that they are somehow difficult to interpret. So not all papers using Siesta are correct. Yes, in fact, most of them have problems. In parallel, we have a Nobel Prize was devoted to density functional because in parallel chemists developed Gaussian codes, which are very important for molecule studying and biosystems. We have several approximations, but we know that all of them give more or less the same results when correctly used, in spite of various technical details. And that was a very, I liked very much this paper published, if I recall well, a couple of years ago in Nature. So the project was to pick up people from all those important codes like Quantum Espresso, Hartree-Fock, and so on. They listed systems that they wanted to study, and they wanted to be quite accurate, the most accurate possible. And it turned out that all those codes give just the same result within the really high accuracy, in spite of different codes, computers, as I said, techniques and so on and so on. So today we have a very nice tool, which is easy to use, but should be used with care. And we have to go beyond density functional theory because the correlations that I have mentioned represent a huge problem, especially in the so-called strongly correlated systems, when we really have to go beyond the mean field approximation, like static problems and so on, and to move to more advanced, one stage higher methods to study those systems. And here I should mention that I have entered the field with Alfonso Balderski, and I had chance for nice cooperations in Poland with Nevil Szwadzki, Paweł Jakubas, Oksana Wolniańska, Tomek Zankrzewski, and Anna Ciechan. And also I profited really a lot from the collaboration with Gary Bernholz and his group, like Marco Nardelli at North Carolina State University. So thank you very much for your attention. I was trying to be rather superficial, but the many body systems are quite complex, and I choose that way. So thank you.